In this class, we learn a new technique for integration called partial fractions. So here are two integrals with rational functions as integrands, fractions as the integrands. Let's discuss what techniques we might use for each of them, but not actually do them. So for this first one, you can remember that this is when you have a single term in the denominator, you can treat this as unadding two fractions together. This is really the integral of x to the fifth over 2x minus 4x over 2x plus 7 over 2x, right? Because when you have the same denominator, when you have common denominators, you can add the numerators. So I sort of unadded this fraction by separating it into three separate fractions with the same denominator. And then you can simplify each fraction. So this becomes 1/2 x to the fourth minus 2 plus 7/2 times 1 over x dx. And then you can just integrate term by term. For b, the first thing that jumps out at me is that I have an x to the ninth and an x to the eighth, which means that I have the derivative of a piece of my integrand also in my integrand. So I'm going to guess u substitution is a good choice. U might be 5x to the ninth minus 1, which means du dx would be 45x to the eighth, which means dx is du over 45x to the eighth. And then I would sub everything back in, and I get 3x to the eighth over u times dx, which is du over 45x to the eighth. And my x to the eighths cancel. And now I have only u's, and I can integrate this as 3 times the 3 over 45 times the integral of 1 over u du, and you would finish it, finish out the u substitution. So rational functions don't always require a new technique, but here is one that does require a new technique. All right, so I want to find the integral of x plus 26 over 2x squared plus 5x minus 12. So the first thing I'm going to do, this is my new technique, I'm not going to do anything with integrals so far. I just want to rewrite my fraction in a simpler way that will make integration easier. I want to rewrite it as a sum of two fractions, and I want the denominators of those fractions to be the factors of my current denominator. So this is going to factor to 2x and x. Boom, I factored it. Okay, so 2x squared plus 5x minus 12, it factors to 2x minus 3 times x plus 4. Do a quick check by multiplying them together. 2x squared plus 8x minus 3x, that's the 5x and minus 12. So this is the goal. I want to rewrite the given fraction, the integrand, as a sum of two fractions where the denominators are the factors of the first fraction. And to figure out what the numerators have to be, I'm going to call them a and b. And I'm going to try to figure out what they are using some algebra. So I'm going to multiply both sides of this equation by the common denominator 2x minus 3 times x plus 4. This is going to clear the fractions. So multiply this by 2x minus 3 times x plus 4, and multiply this side by 2x minus 3 times x plus 4. Okay, on the left, my denominator cancels, and I get x plus 26. On the right, when I distribute the common denominator to the a fraction, the 2x minus 3's cancel, and I get a times x plus 4. When I distribute the common denominator to the b fraction, the x plus 4's cancel, and I get b times 2x minus 3. Now I want this equation to be true no matter what x value I choose. So I'm going to choose a couple of x's to give me some equations. I can choose any x I want. So let's choose x equals 0, because the idea is I want this to be true. I want to choose an a and a b so that this equation is true no matter what x value I choose. So if x is 0, the left-hand side of my equation is 26, and the right-hand side of my equation is 4a minus 3b. So I have an equation with two unknowns. If you have two unknowns, you need two equations. So I'm going to pick one more x value. Let's pick x equals 1. I like 0 and 1 a lot. They're just pretty easy to work with. So x equals 1. 1 plus 26 is 27 equals 5a minus b. So I have two equations with two unknowns. I should be able to solve this using some technique I've learned in the past. I'm going to do substitution here because this equation tells me that b is equal to 5a minus 27. And then I can go up to this equation and replace the b, substitute the b with a 5a minus 27. So I have 26 equals 4a minus 3 times 5a minus 27. And that becomes 26 equals 4a minus 15a plus 27 times 3. $81. Okay, so 26 equals negative 11a plus 81, and 11a equals 81 minus 26. $55. So I get a equals 5. And then to get b, just go to the other equation, and we get b equals 5 times 5 minus 27. So b equals negative 2. All right, so I have done nothing so far to solve the integral. All I did was rewrite the integrand as a sum of two fractions. So now I know that a is 5 and b is negative 2. So I was able to rewrite the integrand as a sum of two fractions. So I need a little more space. We can go to a new page. So the integral of x plus 26 over 2x squared plus 5x minus 12 dx, I can now rewrite as the integral of 5 over 2x, what was it? Minus 3 plus 2 over x plus 4 dx. Now this I can break into two integrals. This becomes 5 times the integral of 1 over 2x minus 3 dx plus 2, oops, it's negative 2. Negative 2 times the integral of 1 over x plus 4 dx. For this one, I'm going to use a u substitution. I'm going to let u equal 2x minus 3, which means du dx is 2, which means dx is 1/2 du. And then this one, I would let u equal x plus 4, which means du dx equals 1, which means dx equals du. So this becomes 5 times the integral of 1 over u times dx, which is 1/2 du, minus 2 times the integral of 1 over, maybe I'll use a different letter for this one since it's a different integral, 1 over w times dw. So this is 5/2 the integral of 1 over u du minus 2 times the integral of 1 over w dw. And then the integral of 1 over u and 1 over w are both ln. So this becomes 5/2 ln u minus 2 ln w plus c. And then replace the u and the w. This was 2x minus 3, and this one is x plus 4. Okay, so the only new thing here is being able to rewrite a fraction as the sum of two fractions. And the idea is that each of those fractions is easier to integrate than the sum together. So the form of the decomposition of a rational function into partial fractions depends on the factored form of the denominator. It will look different for unique linear factors, repeated linear factors, and irreducible quadratic factors. So for each factor that's linear, you should include a partial fractions of the form a constant over that factor. So in our example, both of our factors were unique linear factors. I had a 2x minus 3 and an x minus 4, an x plus 4. So I had a factor of a constant over 2x minus 3, one of my linear factors, and then another over the x plus 4. If you have a repeated linear factor, you have to include it once for each exponent. Okay, once for each power. So you need a constant over x minus c, then a constant over x minus c squared, and then a constant over x minus c cubed until you've hit the exponent n. And if you have an irreducible quadratic, it cannot factor, then you need to put a linear term on top of it. Okay. So this example involves partial fractions of all types, and you probably won't see anything this complicated, but I have a unique linear factor x minus 1. So I have an a over x minus 1 in my decomposition. Then I have a repeated linear factor x plus 1 squared. So I need a constant over x plus 1 and then a constant over x plus 1 squared. And then I have an irreducible quadratic x squared plus 4. You can't factor that any further, so I need a linear term on top of the x squared plus 4. The general procedure for this is on page 7 of the packet, in case you need it for reference. All right, I'm going to set up a partial fraction decomposition for this integral. We're not actually going to find the values of a and b, etc. here, but you will on a similar problem in the activity. So I have 2x squared minus x minus 1 over, hopefully they already factored the denominator for me. So I have x squared plus 1, an irreducible quadratic, x minus 2, a unique linear factor, and then 3x plus 4 cubed, a repeated linear factor. So for each factor, I'm going to have a fraction in my decomposition. So for my irreducible quadratic, x squared plus 1, I have to put a linear term on top, so ax plus b. For my unique linear factor, I just have a constant on top, c. For my repeated linear factor, I need to have a fraction for the linear factor, another one for the linear factor squared, and one more for the linear factor cubed. If that 3x plus 4 were to the fourth, I would need one more for 3x plus 4 to the fourth, and I just need constants on top of each of these, d, e, and f.